Hello folks, welcome to today's video. In today's video we're going to continue going with the inscribed and central angles. We're going to look at some example problems that might use some of these things we've been talking about. So here's an example right here. Rectangle ABCD has its vertices on a circle with radius 8.5. So from the center to any of the corners of our rectangle is 8.5 centimeters. The width of the rectangle is 10 centimeters. What is the length? Right? So this is one of those questions where it might seem like, okay, well, I don't really know where to go from here. But what we can do with these questions is we're allowed to add lines, right? We can increase the amount of information in our diagram by making some inferences. And one of them is to recognize that this 8.5 here is a very special line. It is a radius. So I am allowed to put a radius anywhere else on my circle, and it will also be 8.5 centimeters. So where would I want to put that radius? Do I want to just put it anywhere around my circle, or is there somewhere in particular? Well, if we think about some of these properties we've been talking about with inscribed and central angles, what I can do is maybe put my second radius right there. Okay? And what that does is it makes a special triangle. Because this line right here is now a diameter, right, then the inscribed angle that is subtended by that arc AC is going to be 90 degrees. So this right here is 90 degrees, right? And why do I care about 90 degrees? Well, now I have a right angle triangle. So I'm looking for this missing side right here of my right angle triangle, and that is going to be my length. And what we know is that for a right angle triangle, a squared is equal to c squared minus b squared. Or a is going to be equal to the square root of c squared. So that's my diameter, or twice the radius. So if my radius is 8.5, then my diameter is 17 minus 10 squared. Right, so if I grab a calculator now, right, if I do 17 squared minus 10 squared, I get 189. If I take a square root of 189, I get a length of 13.7 centimeters. Right, so that's all we're going to do in this video. We're just going to go through some example problems, and yeah, that is it, right? So here's another example of a question. If I'm looking for the value of x here, again, what we need to do is try to find the arcs that are making these angles. We know that this 130 is a central angle, and we know that this x is an inscribed angle, and again, because they are both subtended by the arc BC, what that means is that x is going to be half of 130. So x is going to be equal to 130 divided by 2, which is 65 degrees. Okay, same thing here. This x is our inscribed angle. Our central angle is a special one, it's 180 degrees, so x is going to be 90. Okay. Sometimes we might need to add some other properties that we should be aware of. So for example, if I have a circle, the number of degrees inside of a circle is 360. So if I already know part of that circle, I can find whatever's missing by taking those values and subtracting them from 360. So for example, 135 and 75 right here is 210, which means that whatever's left down here has to be 360 minus 210, right? So if that's the case, let's find x, y, and z from this diagram. Okay, so knowing that this angle here is 100 and that this angle here is 140, then from my 360, what I already know is I know 240. So then x is going to be equal to 360. Take away the 240 that we already know, 240, and we get 120 degrees. All right, so from there, let's find y and z. Now, y is this angle right here. And there's something special about this angle right here. If I focus in on triangle A, B, or A, B, O, right? This is a special type of triangle. Why is this a special type of triangle? Well, this side length is a radius, and this side length is a radius. So what that means is that those two sides are the same length. And a triangle with two equal length sides is called an isosceles triangle. And what we know about an isosceles triangle is it not only has two equal length sides, it actually also has two equal length angles. Okay, so if the angles inside of this triangle have to add up to 180 degrees, that means 100 plus this angle needs to be 180. Now, knowing that these two angles are the same, what I can do is I can figure out what these two angles are going to be by subtracting 180 by 100, and I get 80. And then y is going to be half of that, or 40 degrees. And then I can do the same thing to find z. Again, this one here, we already found it to be 120. So I can take 180 and minus 120 to find 60. And what we'll find is that z is going to be half of that, or 30 degrees. Okay, so in here again, finding those inscribed and central angles. So my inscribed angle here is angle DFE, and my central angle is going to be angle DOE. Notice that my inscribed angle and my central angle start and end at the same place. That's really important. They start at D and they end at E because they are both subtended by the arc DE, right? So it's really important to be able to do that. So in the next one, same thing, right? Where are my inscribed angles and my central angles? Well, my inscribed angle is at PRQ, and my central angle is at POQ. And again, look, the P's are the same, the Q's are the same, right? Because again, they are both subtended by the arc PQ. And then again over here, if I found my inscribed and central angles, my inscribed angles are NJM, and there's a second one at NKM. And my central angle is at NOM. And again, just like with the previous two, every single one of those angles, whether they're circumscribed or whether they're central, always start and end at the same place. Starts at N, ends at M. Starts at N, ends at M. Starts at N, ends at M. Right? All right. So let's take a look at a couple more of these questions. So again, just applying these ideas. We already did this one. We know that X is 65. So it might be worthwhile to just pause the video right now and try a few of these on your own. So for this one over here, right? So again, if you want to pause the video and try it first, and then we'll watch the answers, that's probably a good idea. But over here, X is 40. They're both inscribed angles, so they'll have the same value, 40. Okay, down here, X is 90, because this is a diameter. And up here, X is 58. Again, because this is inscribed and this is central, so it will be double. All right, so one more question to go over. Like I said, if you'd like to pause the video, try it first, and then we'll go through it together, right? So here's A and B. Here's question C. So question A, we're looking for the values of Z and Y. So here's my A, B, there's my arc, right? That's subtending all of those angles. So notice that this angle Z has the same arc as 70, so the Z is going to be equal to 70. And the Y also has the same arc, but it's central, so it's going to be 140. Okay, we come down here. What we know is that this right here is 180 degrees. So if this is 50, then Z is going to be equal to 180 minus 50, which is 130 degrees. And again, this is an isosceles triangle. So Y, we're going to find it by taking that 180 and minusing the 130, and we get 50, and Y is going to be equal to half of that, so 25 degrees. Okay, down here, something very similar is happening. Here's one of my arcs, and here's another one. What we notice is that we actually have two arcs here, both having different inscribed angles. So this arc down here has an inscribed angle at 42 and one at Z, so Z is going to be equal to 42. But this arc up here has an inscribed angle at Y and at 27, so Y is going to be equal to 27 degrees. So you can have different inscribed angles within the same circle, but all inscribed angles that are subtended by the same arc will be equal. Okay? Okay, so that's it for today's video. Just went over a couple of examples, and I will see you all in the next one.